All right, hello class. Uh, Mr. Pettibone here, and hey Rowan. Um, Today we're going to be talking more about special relativity. In order to understand today's lesson, you need to know a little bit about matrices. So I'm going to teach you how to multiply a matrix by a column vector. So I'm going to teach you. So this is a fly. So how do we take a matrix and multiply it by a column vector? Okay, take these two, multiply them together. So when you take a matrix and you multiply it by a column vector, the result is going to be another column vector. Okay. Let me make a matrix, and I'm only going to teach you this for the 2x2 case, a 2x2 matrix, because we're dealing with, even though space-time is four-dimensional with t times t, x, y, and z. We're only dealing with sort of like two-dimensional special relativity, so we only have t and x. So what if I have a matrix 1, 2, 3, and 4? So this is a 2x2 matrix, okay, because it goes across 2 and down 2. And then I have a column vector, so maybe it is -2 and 5, something like that. So how do I multiply these two together? They're going to be equal to, so when I multiply these two together, I'm going to get another column vector. And I don't even know, do you guys even learn about matrices? If you don't, you should. They're incredibly useful. So what you want to do is, if I want the top number here, okay, I go across the top row of the matrix, and then I go down on the column vector. So I do this kind of a motion. All right. And so I'm going to do first number times first number plus second number times second number. Okay, so like that. All right. When I multiply matrices together, actually, I don't think I've ever taken a class where until I got to college, but I knew how to multiply matrices in high school because I got this book on it. And the method that made the most sense to me was to just do this with my fingers. So I don't know, that's how I think about matrix multiplication, because that was the way that I made sense of it in high school. So I do first number times first number, so you get 1 times -2 plus second number times second number. So 2 times 5. So that gives me 10 minus 2. So that first number is 8. Okay? Now, if I want the bottom number here, then I'm going to go across the bottom row, not the top row. And I'm still going to go down the column vector. So again, I'm doing this. So when I think about multiplying matrices, I'm always doing this in my head. So first number times first number is 3 times -2. Second number times second number is 4 times 5. So we have 20 minus 6. That would be 14. So the product of this matrix with this column vector is the column vector 8, 14. Okay? Let me see who's here. Hey Rowan, hey Mina, hey Luigi, hey Zach, hey Sebastian, hey James, and hey Fu. All right. So this is your little tutorial on matrix multiplication. So I'm going to move on. Okay. And for this lesson, we are going to choose our units. So we can choose a different unit of time besides the second. And this is commonly done in special relativity. For this lesson, we are going to have c equals 1. Speed of light equals 1. Okay, so we've redefined our unit of time so that the speed of light is now 1, not 3 times 10 to the 8th. Okay. So in particular, that makes our space-time interval, which was equal to c squared dt squared minus dx squared, that makes it just dt squared minus dx squared. So it simplifies it. Okay. So, and then I'm going to define some quantities. Okay. I'm going to define beta, the relativistic beta, which is v over c. So the speed of the object divided by the speed of light. So your beta is always going to be less than or equal to 1 because nothing can go faster than the speed of light. Or I should say that absolute value is less than, because you can go negative, of course. All right. So beta is, so that's the relativistic beta. Basically, it's your percentage of the speed of light. So if I say beta is 0.9, that means that you're going 90% the speed of light. If I say beta is 0.75, you're going 75% the speed of light. All right. And then there's this thing called the relativistic gamma. This is the Greek letter gamma. And it's equal to 1 over the square root of 1 minus beta squared. Okay. All right. So, okay. So one of the things I want to point out is that what is the relativistic gamma if you are at rest? If you're at rest, then your velocity is 0, which means beta is 0. So what is gamma evaluated at beta equals 0? You'd have 1 over the square root of 1 minus 0. So you'd have 1 over the square root of 1, which is the same thing as 1 over 1. So it's just equal to 1. Okay? What is gamma if you were going at the speed of light? So what if beta equals 1? Then you would have 1 over the square root of 1 minus 0. So you'd have, 1 minus 1. So you'd have 1 over 0, which is infinity. So basically, gamma, as you approach the speed of light, gamma approaches infinity. Okay, so if we were to look at gamma versus beta, it starts out at a value of 1. And then as you approach the speed of light, it has a vertical asymptote like this. And it's not even defined for beta larger than 1. Okay? So what we have is that gamma is always larger than or equal to 1. Okay? So these are just some definitions. that are used all the time in relativity. So, what if a particular observer sees the separation between events as delta t and delta x. Okay. Another observer in relative motion will see a different separation between events. Which I will call delta t prime and delta x prime. Okay? So the space-time separation between events depends on the observer. Okay? And so there is a relationship between delta t and delta x and delta t prime and delta x prime. Okay? So the two are related by what is called a Lorentz transformation. And if you're reading some basic textbook on special relativity, it'll just give you the formula for delta t prime and delta x prime. But really the easiest way to remember it is to think about it in terms of a matrix multiplication. So that's why I taught you about matrix multiplication, because you can memorize the matrix for Lorentz transformations really easily because it's a very symmetrical matrix. So I've found that it's easiest to do it this way. So basically what we want to do is we're going to make a column vector out of delta t and delta x. And we're going to make a column vector out of delta t prime and delta x prime. And we're going to multiply it by the Lorentz transformation matrix, which is gamma minus gamma beta minus gamma beta gamma. Okay, so see how that's a nice matrix. Okay, and so basically, so gamma and beta are defined by these formulas right here. Okay, oh, right here. So beta and gamma. Okay, and so the velocity here, this beta is the velocity of the second observer relative to the first observer. Okay? The velocity of the second observer relative to the first observer. Okay? So what if I actually do this matrix multiplication? So what is delta t prime? What is delta x prime? Okay. So what I want to do is carry out this matrix multiplication. So I kind of go like that. So the first row is going to be gamma times delta t. And then I have minus gamma beta times delta x. Knock it off, bug! And then if I want the delta x prime, I have delta t times minus gamma beta. Okay. Plus gamma times delta x. All right. So this is the formula for the Lorentz transformation. Okay. So what that means is that delta t prime equals, so if two vectors are equal, then that means that they have the same components, right? So that means that delta t prime equals that, delta x prime equals that. So I have delta t prime equals gamma delta t minus gamma beta delta x, and I have delta x prime equals minus gamma beta delta t plus gamma delta x. And I encourage you, if you're hardcore into physics and you want to actually like really learn special relativity, to memorize the Lorentz transformation in its matrix form, because it's much easier that way. So don't remember these formulas. Remember just this. This is a lot more visual, a lot easier to remember. Okay. So why is this the relationship? Okay. Why? Why is this the relationship between the space-time separation of one observer and another observer? Well, let's consider a light-like separation. So suppose that and recall, a light-like separation means that 0 equals delta t squared minus delta x squared. Okay, the space-time interval between the events is 0. So in particular, that means that delta x equals delta t. Okay, which means that delta x over delta t equals 1. So it means that the velocity between the events is the speed of light. Okay, so let's suppose that's true. Okay, then what would be the velocity measured by the second observer? So the velocity measured by the second observer would be delta x prime divided by delta t prime. Okay, so that would be minus gamma beta delta t plus gamma delta x over, so again, I'm just reading off this formula here, gamma delta t minus gamma beta delta x. All right. Now recall, because delta x and delta t, it's a light-like separation, then that means delta x equals delta t. All right. So that means that I can go ahead and factor out. So this is equal to minus gamma beta delta x minus gamma delta x over gamma delta x minus gamma beta delta x. You see? Delta x is equal to delta t. So notice how every single term has delta x in it, which means that I can cancel all of the delta x's, and I get minus gamma beta minus gamma over oops, that should be a plus, my bad. over gamma minus gamma beta. So you can see that that's equal to 1. Okay? The numerator is just the denominator written in the reverse order. Okay? So what that means is that if observer 1 sees something moving at the speed of light, then observer 2 sees the thing moving at the speed of light. The speed of light is the same for all observers, okay? And so this is actually an experimental fact, okay? This is an experimentally measured fact. Okay? So I don't want you to think that the theory says what reality is. Experiment says what reality is, and we wrote the theory of, or Einstein wrote the theory of special relativity because it matched experiment. Okay? We know experimentally that everyone who is measuring the speed of light, everyone gets the same answer, no matter what, no matter how fast they're moving. Okay? Think about how weird that is. If you are on an airplane and the airplane is traveling at the speed of sound and there's a sound wave next to you, you're going to be going the same speed as the sound wave. So the sound wave will ride right next to you. But if you're riding next to a beam of light, you're going to see the beam of light go at the speed of light, no matter how fast you're going. So it's a weird fact about the speed of light that even if you're trying to catch up to a speed of light, a beam of light, it's always going to go away from you at the speed of light, no matter how fast you're going. Okay. What was the experiment that established this? It was called the Mickelson Morley experiment. And you can look it up if you're so inclined. But basically what Mickelson and Morley did is they measured the speed of light at different times of the year. And they were like, okay, the Earth is moving in different velocities through outer space. So if we measure the speed of light at different times of the year, we should get different answers because the Earth is headed in different directions. So it's going to be, so the relative speed between the Earth and light is going to be different. But what they found is that the speed of light is the same at all times of year. And so everyone sees the speed of light with the same, have the same velocity. Okay? Zach says, then isn't light going faster than the speed of light? Well, okay, so nothing with mass can achieve the speed of light. So, and the theory of special relativity is kind of talking about light and not light. So you and I, so that's a really good question. Is light going faster than the speed of light? So what if, so for example, this is a really weird fact about special relativity, okay? So for example, what if I'm sitting here and I'm watching a beam of light go by? So this is observer 1, is watching a beam of light go by at speed of light. And then there's an airplane okay? And the airplane is traveling at 99% speed of light, okay? So observer 1 is going to see the relative velocity between the two as 0.01 the speed of light, okay? But here's the trippy thing. What if we thought about this from the perspective of the airplane, okay? Is the airplane going to see the beam of light getting ahead of it at 0.01% the speed of light? No. They will see the beam of light pass them at the speed of light. Okay? Okay, so this is observer 2. So this is the trippy fact about special relativity, and it takes some study to really even appreciate how trippy that is. But the reason that is true is because the rate of flow of time is different for O1 and O2. Okay? See how the rate of flow of time, according to the Lorentz transformation equation, the rate of flow of time is different. See how this has a delta t prime, and this one has a delta t, but this has a gamma in front. So the rate of flow of time is different depending on who you are. Okay? So let's do a mathematical example. Just to kind of establish the rules here. Suppose that Christian asks, does that mean that observers in the plane are seeing the future when the light ray passes by? No, they are not. Suppose that delta x, or delta t and delta x, in one frame are, let's say, 8 meters of time separation. Again, the speed of light is 1, and the only way the speed of light can be 1 is if we measure time in meters. Okay? So that in most special relativity textbooks, we measure time in meters. Okay? And then what if the delta x is minus 3 meters? So really quick, this is a time-like separation between events. Okay? Why do I say that? Why is that a time-like separation between events? It's because the delta t is bigger in size than the delta x. Okay, so the time component dominates over the space component. In fact, you could show that ds squared would be 8 squared minus 3 squared. So that would be what? 55 meters squared. Okay. What would be the separation vector according to another observer with velocity, I should say beta, equals minus 0.95. So the fact that it's minus means that the observer is going to the left at 95% speed of light. Okay? So the first thing we want to do is we want to construct the Lorentz transformation matrix. And to do that, we need gamma. So gamma is 1 over the square root of 1 minus negative 0.95 squared. And so we get that gamma is 3.2. So the Lorentz transformation matrix is gamma minus gamma beta minus gamma beta gamma. So this is going to be 3.2 minus 3.2 times minus 0.95 minus 3.2 times minus 0.95, 3.2. So that's our Lorentz transformation matrix. So what it is it's going to be the matrix 3.2, 3.0, 3.0, 3.2. So notice that the double negatives make the off-diagonal terms a positive. Okay? So then our delta t prime and our delta x prime are going to be 3.2, 3.0, 3.0, 3.2 times the vector 8, negative 3. Okay. So if I do the multiplication, then that means the top number is going to be 3.2 times 8, and then plus 3.0 times negative 3. And then the bottom is going to be 3.0 times 8. Plus 3.2 times negative 3. So working that out, we get 16.6 meters and 14.4 meters. Okay, so it's kind of interesting, right? Observer 1 sees the events as being separated by 3 meters. Okay, one event happens 3 meters behind the other. But for observer 2, one event happens 14 meters ahead of the other. So the locations have swapped. Okay, one is happening ahead of the other in space. So you're going to do one of these calculations, and for your daily item, and I hope it'll be enlightening. Get it? And I will talk to you guys tomorrow with, we're going to talk about Lorentz, what's called Lorentz contraction and time dilation. Okay? So